Hello, everyone. In this lecture, we want to discuss Circom programming. So Circom programming is especially to writing and designing circuits that could be implemented by Growth 16. So to overview discussion, we need to first uh, discuss the scenario again. So you remember that this was the architecture of the Gauss 16, right? We defined the puzzle into a circuit using constraint system and then convert the constraint system into matrix and then use Lagrange interpolation to convert to the polynomial and then using equality test and pairing we generate proof and verify the proof. We discussed the ZK auction when companies apply for the project, and then this function was run by the auction man to compute the uh, final grade for the companies, right? So you remember that the first step in using growth was to convert the function or the puzzle or the scenario into some constraint system code, right? Now we want to do the same thing in Circom, but first let's open the file of the Google Colab. So let's see our website. Yeah, here on the Colab implementation. So this was the ZK auction code, right? So we also saw that in our uh, Python code, similar to the mathematician, we need to define the constraint system here, right? And we discussed that when we want to design a different scenario, we need to update this constraint system. Okay, now we want to see how we can do something in Circom. So in Circom, we do the same thing. We write some line of code to describe the constraint system of the scenario. So this is the code. So this is the code that I have written in VS Code, and this code is describing the ZK auction in Circom program. Okay, so let's review the code very quickly. So these are the input uh, signals, X1, X2, and X3, right? So this was X1, X2, and X3. And also this one as another input, and that is the final grade, right? Y. So we define some intermediate signals also, V1, V2, and V3. And now we have the constraint lines of code. So this is actually the first one. So this is the second one. This is the third one. And now this is the almost final one, right? We consider this definition as a result and then use this triple equation to see that if the result equals to y or not. So here the prover when run this code into the output like 14 as the y. So that's the reason the y is also considered as input because the prover needs to enter the output of the circuit as an input to the code. And then finally, we check that if this input y equals to the result, the value that is computed after running this circuit, after these lines. Okay, now we want to see this code in the VS Code. We have a folder that consists of multiple files. So circom.exe is a compiler that run the Circom code. Makefile is the list of command that we use to run the code. This is the Circom code that specify and describe the scenario. And this is a JSON file which consists of the input of the circuit, right? So the first input is 1, x2 is 2, x3 is 2, and the output is 14. So based on the circuit for the first company, the auctionman will enter the 1, 2, 2, and 14 as the input to this code, and then will generate the proof, and it would be sent to the verifier. Okay, so yeah, so let's see the code here. Yeah, this is the code also. In addition, other than defining the inputs in the component main, you need to define the value of the inputs that could be public. So the value of y should be public because this value also would be sent to the verifier. Okay, now we want to check and run this code and see what's happened and compare it with the computation that we discussed in previous lectures. Okay, so let's go back to the PowerPoint. And now, okay, so this is the circuit and the Circom code. And you remember that we had the three-party in our scenario, a trusted authority that run a key generation algorithm, and this like decide the elliptic curve, the prime value, and then generate the SRS values, right? So for our mathematical computation, the elliptic curve formula was x to the power of 3 plus x plus 9, right? But in previous lecture, we mentioned that for real implementation, we have some other elliptic curve with big values of prime number, right? So in our Python code, we had the same curve and the prime value. So now again, I'm going to go back to the Python code also. Yeah, this is the curve BN 128, and this is the value of the prime number, right? 218 blah blah, and at the end 617. So we have the same prime value in Circom, and the same formula for the elliptic curve. Okay, now we want to, okay, sorry for multiple switching between different files. I'm gonna try to manage the idea discussion from different concepts here. Okay, now after the trusted authority generates the SRS parameters, the prover computes the proof value that you remember. Those were usually the commit values, right? Using the SRS values. So this is the first part of the proof, the second part, and so this is the other part. Yeah, and this is the other one, and this one, right? And the verifier also do a pairing computation for the left side and the pairing computation for the right side. And if they are equal to each other, verification is passed. Now, in previous lecture, you saw that how we had the same scenario in the Python code. Now we want to do the same thing for this file, for the Circom code. So for running the Circom code, first we need to run this command. So if we run this command, we will convert the Circom code into a R1CS file, which usually is kind of a file that translates the constraint system in matrix or in uh, polynomials and something like that, right? Okay, so now we want to run the first command. And in here, we also had the list of command also. So by this command, if we run this command, okay, so after we run this command, so this R1CS file is generated. And so we see that the number of constraints, nonlinear constraint, is 4. So here we also see the nonlinear constraint, and they are 4. And we also had 4 gates in the circuit, right? They are completely similar to each other. Okay, for the second line, for the second command, the trusted authority need to run this code, to run these lines, and then after that, and it will decide the value of tau, right? You remember that we had a secret value of tau that allowed to generate the SRS values. So this line of code is to deciding the random tau value, and then the next line. So in this line, the trusted authority will remove the tau value, because you remember in previous discussion that we mentioned trusted authority should not share these secret values with the prover or the verifier, right? So that's the reason the trusted authority will remove this file. And then the trusted authority will run this code to generate the prover key. So what is the prover key? The prover key is the list of SRS and all of this information that are needed by the prover to generate the proof, right? So that's the reason this this file would be sent to the prover. And the next line is let me remove this one. And the next line would generate the verification key. And what is the verification key? That is the information that verifier needs to run the pairing, right? So in the pairing, we have some parts that are not generated by the prover, right? Like this value and this value. This value are not sent by the prover. This value are generated in the key generation round. So here, right? So for instance, these values should be sent to the verifier, and the list of all of those information that verifier needs to run the pairing are collected into the verification key. So the trusted authority would share this verification key with the verifier also. Okay, so let's run these parts first, and then we will come back to this slide and discuss about the proof generation and verification, right? Okay, so now we want to come back to here, and then we want to run the list of code. Okay, and then this one. And then next code. Okay, so this is the TAW file, right? Let's see if the TAW file is removed. Yeah, we see that with running this line, the secret value are removed or burned. And then this is the proof key. And then the next line, verification key, right? This line also should be listed here. Okay, the proof key and verification key are done and sent to the prover and verifier. So let's see what are the information inside this file. So for example, the proof key. So the proof key is not shown here, but the verification key. Yeah, so the verification key could be written at the witness. No. Okay, so let's discuss the verification key to see what is the list of information that are sent to the verifier, right? So the protocol is gross 16. A curve is defined this one, BN 128, similar curve that we used in our Colab project. And then the number of public elements is 1 because just Y is public. And then this is alpha, and this is beta, and this is gamma, and this is delta, right? And this is another alpha beta values. So let's go back to the SRS to see what are these values. So here, let me remove this. Yeah, so here we see that we have an alpha, beta, gamma, and delta values. And all of these values here, here, and here, and here, they are needed by the verifier to run the verification code, right? So that's the reason these values are shared to the verifier. Other than this, we see that the value of beta, for instance, uh, yeah. So first, let's see the value of alpha. So in the mass, we see that alpha is an element from group G1, right? Because it is multiplied by the generator of group G1. So then it would be an element from group G1. And we know that the elements in group G1 just had two values to show the number, like X and 1, right? So that's the reason we see here two elements for the alpha G1. For the second parameter, beta G2, so beta G2 is an element from group G2, and we remember that we had 4 values to show uh, those elements, right? And now we see that we have four values to show the elements of the group G2. These are four values, right? So the gamma G2 also is 4. So yeah, here gamma G2 also is an element in group G2, so it needs four values to be represented, and also the delta is four elements are needed, right? So we have also alpha beta that has 12 values to be shown, and so I don't know what is this value honestly, but it should be a value from the extended field of degree 12 or something like that, right? Okay, now we saw that the verification key. So the proof key, it is not shown here, but we know that the proof key would be so bigger than the verification key, right? Because all of this value should be in the file of proof key. Okay, we have discussed this, and now we want to see the next steps. So the next step is running some code by the prover to generate the proof, and by the verifier to verify the proof. Okay, so we already mentioned that the prover has a file, a JSON file that consists the input of the circuit. And the red highlights show that this is the secret that prover doesn't want to share it with others. So prover will run this line of code, and then it will run this line of code and send these two files to the verifier. So these two files are actually the proof, right? So they are these files, right? So these files, we should be able to see these values in these proof files, right? So after these proof values are sent to the verifier, then the verifier would run this code that consists the proof and also the verification key. So these values are recorded in the verification key, and these values as the proof, and then this line actually run the pairing computation and check that if these pairing values are equal to each other or not. Okay, so now let's go back to the VS Code and run uh, this code and see what happened. Okay, to generate the proof, and then we want to verify the proof. And okay, so this okay means that the verification test is passed, and the verification, as you know, is computing the pairing, right? Okay, so let's see what are the data in the proof, right? So in the proof, we see that the PI, so this value, this is actually a commit And also we have another commit that is shown by 4 data. And also we have a third commit that is shown by 2 data. So this means that we have just 3 proof, right? 3 values, 3 commit values as the proof. So let's go back to the proof and see what are the proof value in the formula, right? So in the formula, we remember that we had 1 commit here, and it is shown by commit A in the file. So this value is actually the first commit in the formula. And we see that this is an element from group G1, and that's the reason we have 2 values to show the element, right? So the second commit is an element from group G2, and that is the reason the second element here we have 4 value to be shown, because this is an element from group G2. And the third element is again a commit from group G1. And so it's shown that all of this value, they are added and they are added to each other to finally generate just 1 point of group G1. And so all of these values, they are actually the third commit, which is this value here, right? And also it is mentioned the protocol as gross 16 and BN 128 as the curve. So these 3 elements, they are the main part of the proof. So in the verification, the verifier will use the first element, the second element, and other elements by the prover, and this element from the verification key, and then finally check that if the pairing value are equal to each other or not. And then we saw that, yeah, the test is passed because the pairing of the 2 pairing were equal to each other from the 2 sides of the equation. Okay, I think that this is clear now how Circom programming is work. So you see that, let's review very quickly again. We just use the VS Code to write our code here. So you see, actually writing this code is something that we have done in the Colab project also. In the Colab project, we just update the constraint system. And now in the Circom, we just write the constraint code, right? And then in the Colab, we run the verification and the proof steps in the code. Yeah. So for instance, here we could run the setup, and then we run the proof generation and verification. And in the VS Code, we use those line of code, and the backend compiler will run those command and computation. Okay, thank you. I hope that it's clear now, and I could connect between the Circom programming, the Python code, and also the manual computation in previous lecture. Thank you so much.